Hey guys, so in this video we will be talking about the double slit experiment, which is going to really take us into what is called the wave-particle duality. And you may have heard of that before, but in this video I'm going to talk about some very common misconceptions about the wave-particle duality, and we'll look at it from a real quantum mechanical lens. Okay, so here's our experiment. We have a beam of electrons, although you can do this with photons, with atoms. They've even done this with buckyballs, which I believe are like 60 carbon atoms. So, and those are like bordering on macroscopic objects that they've shown quantum mechanical behavior with. So, what we're going to do is we're going to fire it at a screen, and we're going to have these two slits, hence the double slit experiment, that the electron can go through. And then there's some variation. So let's say we block this slit. And now, right now, we're going to look at what would happen if we only had classical mechanics here. Okay, so we're going to block this slit. What's going to happen? The electron can only go through this one. And again, there's going to be like a range, right? A range of possible places the electron can be, because it's not like a completely, you know, we're firing it off. It's not at like a one succinct beam. And so we fired off, the electron can only go through this slit, and we'll see a distribution that looks something like this. Would be our distribution of electrons if we block this slit. Similarly, if we block the other slit, we'd get that distribution over here, and it should be like a normal distribution, symmetric. Okay, so we've got that. Now let's look at what's going to happen, what would happen classically. Don't want that. Okay, what would happen classically if we have both slits open? Well, we'll have the electron will either go through this one or this one, and so then we'll have some distribution like this, right? We'll have lower in the middle again. At this should be more symmetric around, you know, it should have some symmetry around there, but not a great artist. But we should have these two different, you know, distributions. They may overlap more depending on how close the slits are together, and we'll see in a simulation very quickly what's going to happen. And you know that we can actually adjust the distance between the two slits and how wide the slits are. Right, but essentially this is what we should get with classical mechanics. Now we're going to run this experiment now with electrons, see what happens when we apply quantum mechanics. And this was done with light in the early 1800s, and this was Thomas Young's experiment that he showed that light acts as a wave. And now we'll show that in fact things we think of as particles act as a wave as well. If you remember in our last video on the photoelectric effect, we showed that things we thought of as waves, light, did act as particles. Now we're going to show that particles also act as waves. So here's our PhET simulation. Again, as always, link is in the description. And let's show what happens with the electrons. So let's put in the slits. We can, you know, adjust their separation. And I'm going to put a, no, not that. I want a barrier. That's what I want. Okay, so let's look at what happens with one. So we see the distribution of electrons, pretty classical actually. However, you'll see that there actually is there actually is a little bit of extra probability here. If we have the brightness up a bit, you'll see that there actually is another peak here. So that's interesting. That's one weird thing, even with a single slit, that we get another peak here that we shouldn't have classically. Okay, so now let's look at what happens if we get rid of this barrier. We have a double slit. So you can't see it super well when we do it like that. Let's see what there we go. So, just as we predicted classically, we'll have two, but wait, we have another peak. So if I graph this, we'll see it better, but let's see what happens. I think this generally looks better if we see it like this way. Right. We'll have more hits right in the middle. Actually, it's not showing up that well. And now you can do this if you send out single particles one at a time. You'll actually see this you know, you'll actually, if you go over and over and over again, you'll see the same pattern. You don't have to send a bunch of them all at once. The other thing you can see is when we can measure where the particle is, right? It is at a single spot, right? When we shoot one at a time, we can measure its position, right? So it is what's called localized. But then if we do this a lot at a time, if we have the double slits, we'd see this this pattern, this weird pattern. So I'm gonna, where we have this extra peak that we shouldn't have, and we can adjust to see if I can get that extra peak to show up a little bit more. Yeah, there we go, right there. This is not what should happen classically. This is definitely not what should be happening. We have these 3 peaks when we really should only have 2. So we can see sort of why this happens if we describe these electrons as waves, where if we show it like this, you can see that these waves are actually interfering with each other. In fact, and if we only have the one slit, we have the barrier, you can see that we have, and if I bring it up a little bit, I have to adjust it a little bit. You can see that there is some interference. This wave is actually interfering with itself. As you know, you have this little thing over there that creates this extra peak. And so we've got 2 things going on. We have interference, we have double slit interference, and then we also have what's called diffraction. And so let's look at sort of what's going on if we plot these. So right now I'm not going to focus on the diffraction. If you want to learn more about diffraction, you can look at the link in the description. But essentially what it is, you block this one off, you're going to get this these extra peaks, actually, right? And that is caused by some of this wave interfering with itself as it goes through. And you can see more of that, sort of the math on that, in the description, but I'm not going to talk too much about that right now. What I want to talk about is this double slit interference, where diffraction is a form of interference, but I think this one is a little bit easier to visually show. So we send the electron through and we can model it as a wave. And so what's going to happen, if we model this as a wave, this will happen, and then it will go through these 2 slits. You'll have something like this. And as you can see, there will be parts where these waves will add up. They'll interfere with each other. So when we have this, what we'll have in our distribution, let's do that in green here. What we'll have here is we'll have, you know, where this should be. And then, but as you see right here, they're adding up with each other. There's, and I didn't draw this exactly how it should be. But hopefully you can see the point that we're going to get this interference pattern. You know, this corresponds there, that corresponds there, and then in between there's this interference that they're adding up with each other, right? And so this pattern that we see, this distribution, can only be explained by saying that the electron really acts as a wave. That there's some wave distribution and they interfere with each other as you go through this double slit, and that is why we get this. If we do this with light as well, you can do this with photons, it shows. You see exactly the same thing. You see this double slit interference pattern. That's how we really saw it at first, that light acts as a wave. You can see this interference effect here too, that there's this adding up in the center that wouldn't be there classically. And so there's 2 things going on. Number 1, the electrons are acting as particles because when they hit the screen, as I showed before, when they hit the screen, they're localized. They are in a single spot. That's like a particle. But there is an interference effect. And before it hits the screen, there's some kind of probability of going through the first slit, going through the second slit, or this interference. There's some kind of probability. It's not entirely localized. So, so we're going to try to explain this now with the wave-particle duality. And so I want to talk about properties of waves and properties of particles in the way that we classically think of them. So let's move this over a little bit. So let's look at waves. These are classical waves. And then classical particles. Okay, so classical waves are what are called non-localized. Okay, classical waves are non-localized, which means just like these waves aren't in one spot. They're in multiple different spots, right? That's what a wave does. It's not in a single spot. Classical particles are localized. They're in one place. Okay. Now, classical waves exhibit interference. Exhibit interference / diffraction. Okay, classical particles do not experience interference. Or diffraction. Okay, and then the last thing that we have between classical waves and classical particles is classical waves are not discrete. Classical particles are discrete. Right? You have a certain number of particles, whereas waves, you don't. You have a wave, right? It's not like there's not like discrete objects in the wave. So these are properties of classical waves and classical particles. But we've seen in these experiments that quantum waves and quantum particles don't fall into either of these categories. But many people say the wave-particle duality, they fall into both categories. That's not true. So now let's look at here. Let's look at quantum particles, which we're calling quantum particles, even though they're not fully particles as we think of them. Okay, so quantum particles are not localized until you measure. Okay, and we can show that by this electron has sort of like a probability, as you can see with this single particle. No, I don't want a detector. I want the add a barrier, and I want double slits. Okay. Or sorry, I don't want the barrier. So we fire the electron. It has a probability cloud, and then we don't know which slit it goes through until we measure. So the electron is represented by this probability cloud until we measure it, and then once we measure it, it's localized. But before we measure it, it is not localized, as you can see. So right now, it looks like it's going there, but probability will say, eventually one of the electrons will be here. There's probability, and actually, I believe this simulation uses some kind of random generator for the probability of the electron. And as you do this enough, I don't know if there's a way. Oh, rapid. There we go. You'll get the distribution that we saw. Again, I don't know why. It's sort of just, it's random that it's not showing up there as much, as much here, but if you do that and if you go to the simulation, you can see that you'll, if you do that enough, which I don't want to do in this video, you'll do that, right? So quantum particles are not localized until you measure. So they're both sort of non-localized and localized, because they are localized once you measure them. Quantum particles do have interference. So it has interference / diffraction. And again, you can look more at interference and diffraction in the links below. I just didn't want to explain that in this video because there's a bit of math, and right now I'm looking more conceptually at the wave-particle duality. But as we saw with the photoelectric effect, right, even things that are waves like photons still come in discrete packets. Okay, so quantum particles with these properties take a little bit from both columns. They're partially localized, partially non-localized, but they exhibit interference, but they're discrete. So they're not waves and they're not particles. They can't be both. They're their own category. Quantum particles are their own category, but they behave, right, depending on the experiment, right? For the photoelectric effect, for example, light behaves as a particle, but in the double slit experiment, it behaves as a wave unless you measure for a single photon. Same thing with electrons here in the double slit experiment. If you are not measuring it, it appears as though, if you're not measuring a single electron, they act as a wave. However, when you measure one, it acts as a particle. So depending on the experimental setup, you may get that wave behavior or particle behavior, but quantum particles are their own thing. They act partially as waves, partially as particles. In the classical sense, their behavior is a mix between a classical wave and a classical particle, and hopefully you can see by how we put that here between sort of comparing classical waves, classical particles, and quantum particles. So that's the wave-particle duality, and that's going to be very important, that particles, in quantum mechanics, our quantum particles act both as waves and particles with some of their properties. But again, it's important to remember they are not classical waves, they're not classical particles, they're their own category. Quantum particles are their own category, but they just have behavior that is similar to both waves and particles. So hopefully that makes sense, and I will see you in the next video.